Yes, sir, we can see.
Yes, sir, we
Okay,
can see.
excellent. Thank you. Thank you. Okay, so what I'll do today is one of the last topics of linear algebra, and then we go towards optimization starting next week. So we will also maybe do a quick recap of everything that we did like so far. So in this particular topic, we were essentially looking at projections. We started with projecting onto a line where it was kind of a bit straightforward that what I was looking for was the projection of B onto the line through a vector A. So essentially, so this is my vector A, direction A. This is my vector B. So I'm essentially looking at this. So this will be my projection vector if I am say in R2 of this form. So this P is x hat times A, which was equal to A transpose B by A transpose A times A. And we also wrote this as A transpose B because whatever is in the numerator is just a number. I'm just having two vectors, a dot product. So A transpose B is A dot B, which is a real number. So I can just rearrange terms to write it something like this. A transpose A. So this was A transpose over A transpose A times B. And this is what I call as my projection matrix P. Okay, that was the easier one, and then we looked at onto projection onto a subspace. Okay, where it was so the P equal to x hat of A during projection of the line now goes to P equal to x1 at A1 in all these directions until xn at somewhere. So this is the projection. This projection will be the closest to a given vector B. Okay. And what we saw in this case was this P was instead of A x hat, it was now a matrix A times x hat, with A being a matrix, x being a vector, and this was also equal. So how did we compute the x hat? So x hat was computed as a relation from A x hat is A transpose B. So this is A transpose A inverse A transpose B. And therefore, the projection matrix P is now A transpose A inverse A transpose. Okay, and what was the significance of projection vector? So this was essentially was useful when we had more number of equations than unknowns, or when the system does not have a solution. So I'm looking at Ax equal to B. So there is no x which satisfies this relation that Ax is equal to B. So in that case, we are looking at the solution which is closest to B, and that solution being closest to B also has a implication on looking at the closest vector to be when we are looking in terms of solutions of equations. So this is the least squares approximation that we had looked upon. Somebody has a question? Okay, so we did this with respect to the least squares, where we were fitting a straight line to a given set of equations. One second. Yeah. No, later. After 3. After 3. After 3 o'clock. Okay. So sorry about that. So, for example, the closest which we were looking at was a problem where I was trying to fit a straight line which passes through the set of points 0, 6, 2, 0, and 1, 0. Right? So essentially, what is the closest line that will go through these points? So this is 0, 6. This is 1, 0. This is 2, 0. What is the closest line that will satisfy these 3 points? So the idea was to minimize. So this is the error in this side. This was the error here, and then this was the error here. So we solved this as some minimization problem. So the error was quantified as ax minus b whole square. And I was just looking at dE by d with respect to, so I'm trying to fit a line y equal to mx plus c, with the unknowns being m and the unknowns being c equal to 0. Okay, and then we had a nice expression to those systems of equations. Right, so this is where we were, and this also has a direct relation to what we do in terms of projection matrix. Okay, so essentially solving the least square also amounts to solving a projection kind of problem. So my solution x hat was so I'm just looking at this projection vector given a b and a. Okay, now so far so fine. We knew how to handle this. We also did a little example which we could work out by hand, and also found out later that this problem actually fits in to I can actually fit a parabola which possibly goes through these 3 points. Of course, that was not our interest. Our interest was to just to fit a straight line. As always in much of these courses, we are looking at how to efficiently compute this. And even though we proved that A transpose A is always invertible, given that A1 till AN are linearly independent, this was always true. So it was not the question about invertibility of this. Of course, in most cases, even my computer doesn't like inverting matrices, so I have to find out something much easier way for it to handle this kind of large computation, especially when you have matrices which are large size, or where matrices are ill conditioned. Sometimes ill conditioned essentially means that you have eigenvalues not 0, but like close to 0, and therefore the inverse might be difficult to compute. Okay, so this is where we'll try to ask a question of how to make this, how to simplify solving this. Okay, so with this in mind, we ask ourselves a question, right? Okay, so is there a special structure? Is there, or can we assign a special structure to A such that the computing of A, it was A transpose A inverse. So I had A transpose A inverse. Here I had A, and then I had A transpose B. Okay, how to simplify this? Okay, assume now A is such that its columns satisfy this. So let's say I have columns from Q1 till Qn, and let's say this Q1 and Q1 till Qn are such that Qi transpose Qj equal to 0 whenever I is not equal to j, and this is equal to 1 whenever I equal to j. Okay, so let's start with the first expression here. So when I say I take any vectors Qi transpose Qj, it essentially means I'm having Qi dot product with Qj is 0, which means these are perpendicular to each other, the vectors Q1 and Qj. And more generally, these are also called orthogonal vectors, vectors which are orthogonal to each other. Okay, so when vectors are orthogonal to each other, okay, we are still interested in this term, right? So what will happen, can say, let me call this as a matrix Q now. What will happen to Q transpose times Q when this thing holds? Can I say that Q transpose Q will just be a diagonal matrix? Okay, because let's say in 2 dimensions I have Q1, I have Q2. So these are my columns, and then I'm taking a transpose of this and multiplying. So I'll have Q1, I'll have Q2, right? Something like this. And I'm doing a dot product with this. So I'll have Q1 dot Q1, Q1 dot Q2, Q2 dot Q1, and Q2 dot Q2. So because of this, that Qi dot Qj is 0 whenever I is not equal to j, I'm just having terms in my diagonal, right? So there will be some term here. The off diagonal will always be 0. And then I have, so that this results in a diagonal matrix. Okay, something I have achieved here, but that's not good enough, because I still, even though computing the inverse of a diagonal matrix is simpler. So suppose I have d1 till dn as a d, then d inverse will simply be 1 over d1 till 1 over dn. Okay, right. So this is nice, but still doesn't solve my purpose too much. Okay, so let me do something else. What if Qi's are such that their magnitude is 1, which means Qi dot Qi will be simply 1. Okay, or Qi transpose Qi. Say Q1 transpose Q1. So these are Q, all these Qs are now unit vectors. Okay, in this case, so I'm now back to here. There's a reason I write a 1 here. So matrices Q whose columns Q1 till Qn are such that any arbitrary Qi dot Qj equal to 0 and Qy dot Qy equal to 1 are now called orthonormal matrices. Okay, when this happens, this is nice. When matrices are orthonormal, what happens to what happens to Q transpose Q when Qi dot Qj equal to 0 and Qi dot Qy equal to 1. So again, I just do, so on my diagonal will be Q1 dot Q1 all the way till Qn dot Qn and zeros everywhere else, because any other dot product will just give me 0. Like Q1 times Q2 or Q2 times Q1, Q1 times Q4, anything where I and j are not equal will always give me a 0. And everything else will give me, because these are all unit vectors, it'll just give me 1. All ones in the diagonal and zeros everywhere else. So this is now my identity matrix. Okay, now this is nice. Okay, now when Q transpose Q becomes the identity, then what is the inverse of Q? So inverse of Q based on this will simply be Q transpose. Especially when Q is a square matrix. Okay, so we get back to what was our expression of interest. So our expression of interest was something like this. I had A transpose, A inverse, A transpose times B. Okay. Now, what I definitely know is that when A is such that its columns are orthonormal, okay, then I just do a Q, I do a Q transpose, a Q inverse, Q transpose B. So all I'm left with now is, because this becomes the identity, I'm just left with something simpler to solve, Q transpose B. Okay. So this is the premise for it. So we are looking now at systems.
Are we assuming A equals to Q?
No, I'm not assuming anything. I'm just okay. I'm assuming that, okay, what if A has a structure like this? Will the computations become easy? Well, the answer is yes. It actually becomes easy based on something like this. If A's are such that their columns are orthonormal, so what we call these are orthonormal basis, where they are not only perpendicular to each other, but also each vector is of unit length. If this happens, then my inverse term simply disappears. Then I have something like smaller to solve. Okay, then we'll see what this actually means.
In this case, Q times Q transpose again becomes I, right?
No, okay. Q transpose Q is I, but Q transpose Q times is I only when Q is square matrix.
Okay.
Okay. So I'll have to be careful of that. If Q is square, then we also look at the special case. What happens when Q is actually square? Okay. Because how was our A matrix, right? When we wrote down the this little problem of approximate, this was our E matrix, right? When I said I want to look at points this and this 0, 6, 1, 0, 2, 0. My A was not, this was not square, no, this was rectangle. So I'm asking that, okay, if I'm okay if A is rectangle, what if it has a special structure? Special structure says that both columns of Q are of unit length and they are also orthogonal to each other. Okay, so this will be the point of discussion now. Okay, so before that, okay, what are these matrices Q, and what are their special properties? Why do we need them, and so on? Okay, so examples of Q, which is essentially you're looking at some kind of an orthonormal basis. Sorry?
Sir, in that example, the A rectangular matrix was not orthonormal, right? So
No, it was not orthonormal. Okay, so the
then
so
how do
the-
we understand that?
Okay, correct. How will you understand that? That's a good question. So what I was okay. We started off with the special case of what if A is in this special structure. Then we concluded that okay, I have a nice much simpler expression to work with. Okay, now the next question that we will ask is if A does not have that structure, can I get it into that structure? Okay, we'll see. Okay, if I give you a system of equations which looks like this, a slight digression, but it's okay. X plus y plus z equal to say 3, y plus z equal to 2, and z equal to 1. Okay, what is the solution to this system of equations? Just do back substitution, right? I know that z equal to 1, then I know in the second equation I substitute for z equal to 1, I get y equal to 1, and therefore x equal to 1. So this is all, this is, given nice structure so that I don't have to invert matrices and all that. I can just do backward elimination. Okay. Now, what if the system is not in this form, right? So if say the system is like x plus y plus z equal to 3, then 2x minus y, sorry, 2x minus y plus z equal to 2, and say y plus z equal to 2, or say something like, okay, 3x plus y plus z is equal to 5. Then what do? I just do Gaussian eliminations, right? I just do Gaussian elimination to get into that kind of upper triangular form. So what I now know is that if I have it in this form, then I can just do backwards elimination to solve the equation. So similarly, until now here I'm assuming that okay, what if A is Q? What is A is Q? Then it simplifies my problem quite a bit, right? It simplifies my problem quite a bit because I can just have, so what was the system of equations that we were looking at solving? We were looking at solving in the least square sense this equation, right? A transpose A x hat is A transpose B, right? And then A transpose A was invertible, so x hat simply becomes, so this computing this inverse becomes much easier. So A transpose A inverse A transpose B becomes simply A transpose B, because this is, now I just have to do I don't have to worry about inverting matrices. I just have to worry about some very simple matrix operation, which is matrix times a vector. This is easy for me to handle, right? This is just like a linear in the number of steps. Okay, we'll come back to that. So I will we will conclude this today's lecture by just asking ourselves, what if A is not in this orthonormal form? Can I do something to get it in that form? And once I have it in that form, then I'll have a little simplified solution. So that is what will be the objective of today's lecture. Okay, now what we just do some examples of these orthonormal matrices. Okay, orthonormal matrices, I said Q is, okay, this is good, right? So I have a cos theta, I have a sine theta, and I have a negative of sine theta, I have a cos theta. Okay, first property, of course, Q is equal to Q transpose. Fine, these are unit vectors because if I call this as Q1, if I call this as Q2, the magnitude of Q1 is 1, and the magnitude of Q2 is also 1. Okay, and not only that, Q1 dot Q2 will always be 0. Okay, so this satisfies a set of things. Q is Q transpose. Okay, and not only that, that Q transpose is also the identity matrix for this. Okay, what does this vector do? If I have a cos theta, I have a negative of sine theta, and a cos theta. And let's say I have a vector 1 and 1. What does this do? So when theta is, okay, let me call this 1 and 0. Let's do this simple, right? So I'm just having a vector here, 1, 0. So when theta equal to 45, okay, what happens to this vector? What is cos of 45? Okay, just I can, maybe I might forget the process in the minus, but just let me know if I'm doing this correct. So this is 1 over square root 2, 1 over square root 2, a 1 and a 0. So this will be this and this, 1 over square root 2 and then 1 over square root 2. It is essentially somewhere here, right? So what this has done is to rotate the Q, rotates the vector 1, 0 by 45 degrees. In general, it will rotate any vector x, y by theta degrees. This is also called in general the rotation matrix, that the magnitude of Q is always equal to 1. It just takes a vector, rotates it by a certain angle given by theta. Okay, second, these are also, okay, we had seen this earlier, right? Permutation matrices. Permutation matrices 0, 1, 0. I can say, okay, 0, 1, 0, 0, 0, 1, and a 1, 0, 1, 0, 0. So this P, what is this is P. The transpose of P will be, I take this first row, put it here, this is 0, 1, 0. Then I have 0 and 0 and 1, and then the third I have 1, 0, 0. So I can check quickly that P is such that P transpose times P is the identity. Okay, so this is the set of permutation matrices are also orthonormal matrices. That kind of is easy to check, and we have already worked with that. So we have seen rotation, we have seen the permutation matrix. It just flips the order of the vectors, and so we can conclude that every permutation matrix is an orthonormal matrix. Okay, last thing, reflection. Reflection, let me see, I take a vector Q, which is identity minus twice U transpose. You can use any arbitrary vector. If so, if U is like this, a vector of this form, U transpose U. So U transpose will be a matrix. Right, I'm just doing a column times a row. Okay, so this is nice. So first check what will be Q transpose. Okay, because what was our claim was that Q transpose Q should be the identity. Okay, Q transpose is the identity minus twice U transpose, the transpose of the whole of things. So I'll have I minus twice U transpose. This is also equal to Q. Okay, and if I multiply Q with Q transpose is 1 minus twice U transpose. Uh, 1 minus twice U transpose. Again, I do this identity minus twice U transpose. I do those steps. So this will be identity minus 2 times this will be 4u transpose plus, now this multiplies this will be 4u transpose. So I get the identity. Okay, so this is nice. So what does it mean by a vector of this form? Let's say I'm looking at the direction u equal to minus 1 over square root 2 comma 1 over square root 2. So essentially, this will be somewhere a vector around this direction. Okay, so what does this operation do? This operation, so if I just take any vector, so q is identity minus twice, u is of the form negative 1 over square root 2, 1 over square root 2, 1 over square root 2, 1 over square root 2. This will be identity minus twice of let me add this a little better. This will be identity minus 2, and I will have minus 1 over square root 2, 1 over square root 2, minus 1 over square root 2, minus 2. So this will be identity minus twice. Everything here will be 0.5, a negative of 0.5, a negative of 0.5, and 0.5. This will give me 0, 1, 1, 0. Okay, in R2. So if I take any arbitrary vector x and y, I multiply this by 0, 1, 1, 0, all I get is y and x. So xy goes to yx. Okay. Just like if I'm here, a 2, 1 vector will go to a 1, 2 along this line. So what you can see that if xy is 1, 1, 1, 1, then I'm just around this line. There is no reflection anymore. So this this particular expression, q is 1 minus 2u transpose. This is also called the reflection operation or the reflection matrix. Okay, so these are examples of q. Okay, so now back to the question which one of you had asked, that I'm assuming that Q has a special structure, that A has a special structure which looks like Q, which is an orthonormal matrix. What if A is not orthonormal? Okay, so we will try to answer that question. So yes, sir, please ask questions.
Sir, how we are taking this u value in the previous example?
You can be any vector. You can be any vector. It will just give you reflection of something. So you can just also take u as 1, 0. I don't know, whatever. Any arbitrary vector can be like a reflection.
Okay. And sir, how we are taking this transpose? How transpose of q is coming as I minus 2u transpose? That is also not clear.
Okay, let's do that. Okay, so we are here. Okay, so I'm wanting to compute q transpose, which is I minus u transpose, the whole transpose. Okay, until this is fine. Okay, we'll use two things here, two properties. I'll erase this for a while, make it a little bigger. And okay, A plus B transpose is A transpose plus B transpose. Okay. Similarly, if I have two matrices, C times D, this will be D transpose, C transpose. Okay. The first term here, I have I. So I transpose will be I minus 2. 2 is just a number. I am looking at U transpose, the transpose of this. So here I am using the first property. Okay, now the second property, I am looking at what is U transpose, the transpose of this. This will be the second term transpose multiplied by the first term transpose. Okay, what is this? I'm taking a transpose of a matrix and taking a transpose again. So I'm left with again U transpose. So this guy inside will simply be 1 minus 2 U transpose, as it was always. Okay, this is how this is kind of straightforward. You can just maybe write it down. It's just a two-step computation.
Sir, just one thing here. So this U matrix is a matrix like about which we want to take a reflection of something, some point.
Yes.
Or what
So
it is
U
exactly?
okay. U is a vector. U like here it
Okay.
was 1 over. Okay, it can be any vector. Just say U1 and U2. And if I do U times U transpose, okay, I'll do it a little better here. U is a vector, right, of this form. Any vector. U1, U2. So how does U transpose look like? U transpose looks like U1, U2, U1, U2. This is U1 square, U1, U2, U2, U1, and U2 square. You get a matrix, right? U transpose. Okay, that is why this here is a identity matrix. U transpose will come across as a 2 cross 2 matrix.
Correct. So basically, like if I want to get reflection of some vector or point like XY, you gave the example. About where, like about what we were looking for reflection, whether that line or vector will be defined by this U or what it is. This means when we are saying reflection, it means like there will be some reference about which we want the reflection.
Okay, so let us take this and compute. Maybe I'll let you do this, right? What was U in my example was
minus 1 by root 2, 1 by root 2.
Minus 1 by root 2, 1 by root
1 by
2.
root.
Okay, let us compute this. No, what will be the reflection matrix? Q was I minus 2.
That came as, yeah.
To
that came
whatever,
as 0, 1, 1, 0.
Yeah,
like the
this
final answer Q was 0,
0
1,
1,
1, 0. Yes.
Okay, so if I take this, so what does this give me, right? So if I take x, arbitrary x and a y, this will give me y comma x, right? If it is, say, let's take 2, 3 numbers, no? 2, comma 1, okay, I'll draw it a little bit to scale here. To say 2, comma 1, it will give me, say, 1, comma 2. Say 3, comma 4 will give me 4, comma 3. So it's just reflecting along this line, which is simply perpendicular to this one, which is negative of this one, 1 over square. So this is my mirror line.
Correct. Okay, so now I understood, sir. Like basically this U will define which one is the mirror line.
Yes.
Yeah, that.
Yeah.
And sir, for this U, it needs to be a unit vector.
U can be whatever. Okay, just for convenience, I'm taking it to be a unit vector.
So U doesn't have to be a unit magnitude, right? It can be anything.
It can be, okay. Okay, if it can be anything, but okay, to make it orthonormal, okay, you may need to impose this condition that U square equal to 1. So U is also a unit vector. Because we want the orthonormality also, not the zero. So U is actually a unit vector.
So let's suppose if we have any other vector, first of all, we need to convert it into a unit vector and then proceed further.
Yes. For example, simple ones you can take are like 1, 0, 0, 1. You can look at 0.8, 0.6, negative of 0.6, 0.8. All this will be unit vectors. And you can see how the projection matrix will change appropriately.
Okay.
Okay. Nice. Okay, so back to where we started off. So what was the motivation? How does this help me solve my least squares? Okay, so I was what was where did I start off with? Okay, we will go back again to the least squares problem, and here I was looking at solving A transpose A x hat is A transpose B. This was what I was looking at, right? And then my x hat was A transpose A inverse A transpose B. Okay, this is what I looked at when I was looking into the projection form, and then my projection matrix P was A transpose A inverse A transpose. Okay, I'm writing this repeatedly. I think that will be useful because we need to really understand carefully of where we are heading by doing all these computations. Okay, so suppose now that okay, P. So if I look at this one, right? Okay. A transpose x hat was A transpose P, and then P becomes Q times x hat, and this projection matrix, the capital P, will be Q, something inverse here, which will just be the identity, times Q transpose. So my projection matrix P will have the form of Q transpose. Okay, what is my so in this case there are no matrices to invert because this becomes the identity. Okay, no matrices to invert. Then the best x hat now will be Q. The best x hat here will be simply Q transpose P. Not this. Right, this is fine, right? The best x hat will now be Q transpose P, which is just the dot product Q1 till Qn times P. Okay, and then the projection vector now P is equal to Q x hat. Okay, so we started off with P was A x hat, and we were computing this x hat. Okay, now what happens to Q x hat? So Q, this will be Q transpose, and B. What are the components of Q? Q is Q1 till Qn. These are all the columns, and then Q transpose B will have these numbers Q1 transpose B till Qn transpose B. So this will be, each of them will be Q1 transpose B plus all the way till Qn Q1 transpose B, assuming A has a structure of Q. Okay. Now somebody asked what happens when Q is square. Okay, when Q is square, then what happens? Okay, let's take a simple example here. When Q is square, let me say that Q1 is 1, 0 and Q2 is 0, 1. These are orthonormal. Okay, then what does Q1 transpose times B give me? That is Q1 is 1, 0, 1, 0 times this vector B. This will be 1, 0, 0, 0 times B plus similarly 0, 0, 0, 1 times B. So this is the 1, 0, 0, 1 times B. Okay, what happens in this case is that P will simply be equal to B, because when the matrix is square, Q transpose is also the identity. Okay, and then this will disappear. So this identity times B will simply be B. So when I am projecting onto the entire space, it essentially means that I am just solving simultaneous equations where where the number of equations will be equal to the number of unknowns. So nothing special there. So when Q is square, then there is no projection, right? So my projection vector is still be the B, and I can find exact solution to AX equal to B, or QX equal to B in this case. Okay, that is not much surprising here. Okay, what will be surprising is when things do not work the way we want, and we need to do some manipulations to get to where we are. Okay, so first is so this will be called as the Gram-Schmidt process. Okay, what does this do, right? So the point of this is that we know that orthogonal is good, but in general everything is not orthogonal. But then I always need to compute A transpose A inverse. So is there any way where I can start from a given A, B, C and transform them to an orthonormal basis such that I'm going from A, B, C to Q1, Q2, Q3, where Q1, Q2, Q3 are orthonormal. What is orthonormal? So I have vectors which are perpendicular to each other and also of unit magnitude. Okay, so let us start with right. So what do I say? Start with 3 independent vectors, A, B, and C. The independence is important here, right? And we want to construct 3 orthogonal vectors. Okay, when I have 3 orthogonal vectors A, B, and C, how do I make this orthonormal? What I do is I take A, I divide this by magnitude of A. I take B, I divide this by magnitude of B. C. This I can call this as Q1, this I can call this as Q2 and Q3, and I get an orthonormal basis. Okay, so first is, so what I want to do is, okay, suppose so this is my A, this is my B. What I know is that I have a projection of B onto A with some error term. Okay, that's where we started with, right? So let's say I just put my reference direction as A. So I don't really need to do anything. I'll just use A equal to A, divide by its magnitude, and then call it Q1. So Q1 is the vector A divided by its own magnitude. Okay, from this A, I want to construct a vector which is perpendicular to A. So what I do, I take the projection of B onto A, and this vector now I know is that E is perpendicular or orthogonal to A. How do I construct that? The vector B, so I'll call this the E as my new vector B, which is perpendicular to A. So B will be B, the original vector minus its error. This error we know, it was A transpose B by A transpose A times A. Okay, this is now fine. So now what do we need to check? Check if B is actually perpendicular to A, then the dot product of A times B should be 0, which means A transpose B, which is A transpose B minus so A transpose B will be A transpose B minus A transpose of A transpose B, A transpose A times A. This will be again A transpose B minus A transpose B will be equal to 0. Okay, so A and B are actually perpendicular to each other. Okay, this is fine. Now, construct a C now, a capital C, starting with a small c and which is perpendicular to both A and B. How do I do this? Again, nice. So C is C minus A transpose C. I'm subtracting first the error vector in the C direction and the error vector in the B direction. B transpose B times B. Okay, now this is the only idea of Gram-Schmidt project. So subtract from every new vector is projections in the directions already set. So I have here A, I have here B. I take this difference to give me these two vectors. Suppose I have a vector. Okay, I don't know how we'll draw this. Let's say somewhere here is C. So I'm just looking at. So this is my A, my B. This is my C. So this will give my capital A. This is my capital B, and I'm finding a capital C which is perpendicular to both these projections on A and B, and that will be given mathematically of this form. Okay, so what does this mean, right? Let us quickly do with the help of a small example. I'm not worried at the moment about my A, B, and C. Okay, so generally these are 1, -1, 0. B will be 2, a 0, and a 2. C will be a 3, a -3, and a 3. Okay, what I want to do is start from these three vectors and then construct three perpendicular vectors A, B, and C. Okay, so what do? I just compute these three expressions. B for here, C for here. So A equal to A. B is B minus A transpose B over A transpose A times A. This will be 1, 1, and a 2. Similarly, C from this formula will be 1, 1 minus 2. C is 1, 1, 1. So starting from A being 1 minus 1, 0, just check if A, B, and C are perpendicular to each other. This is 1 and 1. Yeah, this is true, right? So A is perpendicular to B, is perpendicular to C. Okay, now I can generate Q1 by just dividing this by its magnitude. So this will be 1 over square root 2. This will be 4, 2 to the 4, 1, 5, and 6, 1 over square root 6, 1 over square root 3. This will be my Q1, Q2, and Q3. Okay, to summarize, when A is 1 minus 1, 0, B is 2, 0, 2, C is 3 minus 3, 3. Q1 is A over magnitude of A, that is, okay, this remains the same just as A, 1 over square root 2, 1 minus 1, 0. Q2 is B over magnitude of B. This is, what is my capital B? 1, 1, -2. Magnitude is 1 over square root of 6. Similarly, Q3 is C over C is, what was my C vector? This is 1, 1, 1. Magnitude will be 1 over square root of 6. Okay, so for now, just before we give the final result, just understand this as constructing Q1, Q2, Q3, given some arbitrarily A, arbitrary B, and arbitrary C. So this Q1, Q2, and Q3 are constructed such that they are orthonormal bases. So Q1, Q3 have magnitude 1, and they're also perpendicular to each other. Until this is fine, then if this is okay, we just give our final punch to the theory that we are trying to develop.
That small a, b, c are how are they related to the capital A, B, C? I'm not following actually.
Okay, so what I'm doing is I am given small a, small b, small c. So I'm constructing capital A, capital B, capital C such that they are perpendicular to each other. So I start with my algorithm will be like this. So the first direction I just fix that I don't really need to. I just fix A as the reference. I will call it capital A. Here this is my reference direction. 1, -1, 0. Q1 will be A divided by the magnitude of A. So that is 1, -1, 0 divided by its magnitude. This is easy, right? Nothing changes here. Now this is my A. B is given to be something like this, but I want to construct a B, capital B, which is perpendicular to this A. Now I know something, right? If I project B onto A, okay, this is a projection vector, but there is this vector which I earlier called the error vector is now perpendicular to A. So given A, I am constructing a B which is perpendicular to A. Okay, now given these two, now I am constructing a C which is perpendicular to both of these three, perpendicular to A, perpendicular to B. How do I do this? I'm just looking at the error vectors each time. This will be the error vector in the first case. No, not this one. And this will be the error vector in the second case. I'm subtracting it from the projections in each direction. Okay, simple, that's all. Nothing else we are doing. I'm just trying to subtract projections of C on A and B to get C. Earlier, I'm just subtracting projections of B onto A to get capital B. And this
And
is
why are you doing this, sir? What is the purpose of doing this?
Okay, what is the purpose of doing this? So the purpose of doing this was that if my A matrix was equal to Q, then my least squares becomes much easier. I don't have to compute any inverses and so on. Okay, so I'm trying to have a much simplified method now to solve the least squares problem without actually having to get into solutions of. So this was my problematic part all the time. So is there a much nicer way to do this? Okay. So using this, okay. So I'll write down the final thing and then we will discuss. Okay. Start from A, B, C. Okay. Then construct capital A, capital B, capital C as, okay, this I leave it as it is. Capital B as B minus A transpose B over A transpose A times A. This is error vector. And then capital C as C minus A transpose C, A transpose A times A. Also, it should be perpendicular to B. So B transpose C, B transpose B times C. Okay. Now, these A, B, and C are now perpendicular to each other. But what I want is I want Q1, Q2, and Q3, which is easy, right? Once I have three perpendicular vectors, what I do is I just take A divided by its magnitude. I take B divided by its magnitude. I take C divided by its magnitude. Done. Okay. Now first is, how do I do this? What is the purpose of doing this? And what does this achieve? So this is called now the QR factorization. Okay, this computation is now easy. What I will do now is to look at each of this as, so A is A. What is A in terms of Q1? So A, Q1 is A times magnitude of A. Therefore, A is Q1 times the magnitude of A. Okay, so I write these three equations in terms of Q1, Q2, and Q3 via these expressions. Okay, now what do I get, right? I will skip a couple of steps to write these vectors A, B, and C will now just be, I have Q1, I have Q2, I have Q3. These are the orthonormal bases which I get. What is pending here is Q1 transpose A, Q1 transpose B, Q1 transpose C. Will be a 0 here, a 0 here. Q2 transpose B, a 0 here. Q2 transpose C, and Q3 transpose small c. So this is called as A is Q times R. Okay, so this is the QR decomposition or the QR factorization. Okay, so start from here that A equal to Q times R. I can also write R now as Q transpose A because Q transpose Q is the identity. I multiply both sides by Q transpose to get something like this. Okay, what happens to now my least squares problem? Least squares problem is now, what was I looking at? I was looking at A transpose A. What is now A? A I can write as Q times R. A transpose A is QR transpose QR. This will be R transpose Q transpose Q times R. This is R transpose R. Okay, now what is the least square? So I'm interested in A transpose A times X hat was equal to A transpose B. This simplifies to simplifies to R transpose R X hat is R transpose Q transpose B. Okay, and then we finally reach now, because of this, R X hat is Q transpose B, or X hat is R inverse Q transpose B. Okay, what is this R? R is now is a upper triangular matrix. Again, computing the inverse of this is much easier. So instead of now solving, AX equal to B, which has no solution, we now solve for Rx hat is Q transpose B by back substitution. Right? This is again in the form of what we had talked about earlier, right? X plus Y plus Z equal to 1, Y plus 3, this is equal to 2, z equal to 1, right? You see that in that very nice form now. R is this one, right? It's in the upper triangle form, same like what we had here. This I can easily solve, right, by just back substitution. Okay, so did we try to answer the question of what if QA is not orthonormal? Well, if A is not orthonormal, I can decompose A into a matrix which is orthonormal and an upper triangular matrix. Okay, and this orthonormal matrix Q is such that Q transpose Q is the identity. Okay, now when I do that, all I now have to solve is an equation of the form Rx hat is Q transpose B. What is Q transpose B? It's another vector. I'll just call this say B tilde. And here I have a nice upper triangular structure which I essentially get from my Gaussian elimination while I'm solving the equation. Okay, so if A is Q in the structure, then I say, well, no worries. Okay, if A is not in Q, if A is not like Q, still no worries, because I can always write A equal to QR. Okay, simple. This is fine.
The size of A can be anything, right? Rectangular matrix or square matrix.
Doesn't matter. Now, once I have a structure like this, I can just do, if I have even 25 equations like this, I can just go backwards 25 times and solve. No computation of inverses, nothing. All I need is just this 25 back substitution methods and just one multiplication of a matrix with a vector.
Sir, by projection, are we not losing any information?
No, by projection, we're actually getting information, right? So when I say I am unable to find solution to AX equal to B, when there is no solution, I just find the closest solution to B. And that closest solution turns out to be the projection. We are losing out information, but because I cannot get, so it's just like fitting those 3 points, right? Point 1, point 2, point 3. Can I find a line which goes through these 3 points? Answer is absolutely no. But can I find a compromise that I find the line from here which will minimize all the errors? Because, okay, I cannot have a line maybe which is like this or like this. So the only compromise is what is the closest? The closest will be the one which maximizes the error, or in the words of projection, this is just the projection of AX. What is AX onto B? What is the closest B that I can get? So that is this. I'm looking at now not an exact solution because I cannot find one. I'm looking at some kind of an approximate solution.
Originally, you had A matrix A into MX is equal to C, right?
No.
So the
which
same
one?
line you were multiplying matrix A into Y is equal to MX. You represented that line by Y is equal to MX, right?
Correct.
So how do so here the same, the M and X, right? The slope and the Y
Yes.
y-intercept
is right down. No. So I had 3 points: 0, 6, 1, 0, 2, 0. Okay, and then I am looking at Y equal to MX plus C. The first equation, Y equal to 6, X equal to 0, and C. Second equation, Y is 0, M is unknown, X is 1. No, correct. No, something like this, right? Okay, third equation, Y equal to 0, X equal to 2, and C is unknown. So I have an equation of the form 6.
Sir, your screen, okay.
Visible or no?
Yeah, now it is visible. For some time it was gone.
Okay, so I want to find a line which goes through these 3 points. So any line which goes through these 3 points can be defined by this. So I'm just substituting for x and y for these 3 different things. 6 equal to m times 0 plus c and so on. Okay, my unknowns here now are m and c. My equation now becomes a 0, a 1, a 1, a 1, a 2 and a 1. So this is a x equal to b. And for this, there is no unique solution. Okay, but what was the approximate solution that we had the other day? We go back to check. Much back. Even before this here. So my solutions here. Okay, I don't want to project this, but I want to. This. Okay, so I was solving these 2 equations, right? So of 3c plus 3m equal to 0, this and this is b equal to 0. Okay, I didn't solve it explicitly, but the solutions here would be just the gotten by solutions of here. So what we could also alternatively check is the following. This we can take the same example. Okay, let me see if I can find the solution for this. Okay, so the solution to these systems of equations came like 3c plus 3m was equal to was equal to 6, and then sorry, 3c plus 5m was equal to 0. Okay, let's not solve this. A transpose A looked like. Again, I had to invert this. So let us go here quickly. I don't know, maybe somebody can help me compute this quickly to see if we can find the QR decomposition for these matrices. So first, okay, so I have A. So small a is 0, 1, 2. Capital A is also 0, 1, and a 2. What will Q1 be? Q1 will be 1 over square root of 5, 0, 1, and 2. Is correct? I'm just finding the unit vector of this. The magnitude of this is 5. Okay, how will I construct B from A? The construction of B from A is again straightforward. Again, I'll just take help of one of you here. So this will be B minus A transpose B over A transpose A times A. So my capital A is 0, 1, 2, and the small b, capital A is, okay, and the B will be 1, 1, 1. What will this be? If someone can quickly compute. B is 6, 0, 0. Okay, this A, I'm looking here at this A right now. Don't confuse with the general A. Suppose B. Okay, let me see if I can use
Like 1, 2 by 5 minus 1 by 5.
how much this will be. Just give me the capital B.
Capital B is 1, 2 by 5
Okay.
minus 1 by 5
2 by 5
minus 1 by 5.
minus 1 by 5. Okay. Okay, then we can compute Q1 and Q2.
So why we have taken small a as the first row only?
So for one direction we will fix, no?
Okay, so then capital B and small b. So small b will be 600 only, or it should be the second column?
No. So here I have two vectors A and B, where A is 0, 1, 2, B is, sorry, this should be B, no, not 600.
So
B is
triple one, right? 1 1.
B is triple one. Sorry. Okay. Notation. Sorry. So given these vectors small a, small b, I first construct capital A, capital B, and then capital A by the magnitude of A, capital B by the magnitude of B.
And sir, one more confusion is like this A transpose B is there. So what is A transpose? Is it a matrix capital A which is there in the question statement, or is it the A that we have constructed right now?
Yeah, so whenever I start from here, I'm just looking at, this is the A which we construct from here.
Okay.
Okay, try working this out. Should be simple.
So you're saying, sir, we need not calculate the inverse of A, right? That's the purpose now.
Okay, with a little effort, we can find that with this, the capital Q will be 0, 1, 0 minus 0.44. So here will be 0 and 0. This will be minus 0.89. This will be minus 0.89, 0.44. R will be an upper triangular of minus 2.23, minus 2.23, 0, 1, and a 0, 0. So I'm just doing the computations and simplifying. We can check this again by ourselves. And the solution, what will the solution finally be? Solution finally will just be R x hat equal to Q Q hat B. So oops. Okay, I think just check this, and we're out of time, so maybe just try to work this out by yourself, because we have done this the same example for the least squares. We also done the same example using projections. So just compare it if we can get the solve it via the appropriate QR decomposition. Okay, and then we'll again try to verify our solutions next time. So this largely ends the linear algebra part of the course. What we will do next time is to slowly go towards solving some simple optimization problems.
Sorry, which problem?
No, the same. No, so just try to solve the same problem of fitting these 3 points into the straight line via the QR decomposition. Solve the same problem, the QR decomposition.
Sure.
Okay, and next time we'll slowly get into optimization and related topics.
LU decomposition also in the similar way works.
LU is much simpler. Okay, we'll try to do that next time. Maybe we'll take some 5-7 minutes to just do that. So
Okay,
if
thank
you're
you.
interested, we can just start with the LU decomposition. It will be a little similar, but we will do it again.
Okay, sir.
Yeah. Okay. Thanks.
Sir, when the assignment will be provided?
Assignment is already posted, right, or not?
No, sir. I mean, I have emailed you and Nandan sir also regarding that, but I mean, I did not
Anik?
receive any response.
So Anik did not post it.
No, sir.
Oh, okay. Let me check that. No, so I will do that because I thought he was posting it.
So, sir, have you received my email? Like, because I did not get any response, I'm just trying to check if my emails are reaching to you or
Yeah,
not.
your answer, right?
Yes, yes.
Yeah. So I will. Okay. So I will try to just again maybe reply to your email. I don't know if. Okay, I'll try to post it myself.
Yes, sir. Yes, sir. Thank you.
Yeah.
Because we
Yeah,
need
no,
an assignment to at least know, like.
I know. I'm sorry.
Yeah. Yeah.
Okay, I'm sorry about that, but I will let me just do it right away.
Thank you,
I'll
sir.
first send you by email so that you can send it to everybody.
Yes,
I'll
sir.
also try
Yes,
and
sir.
upload it on the portal.
I can do that. Sure, sure. Thank
Okay,
you, sir.
yeah, thanks. And then apologies for that.
Yeah, yeah. No problem.
So one question, the quiz will be multiple choice, right?
Yeah, we'll just do multiple choice. It will be multiple choice, multiple select, and some short answer questions where you have to calculate something and punch in the answer.
Okay.
Yeah. Okay, good. And I'll just try to do the assignments right away after this call.
Sure. Thank you, sir.
Yeah, thanks everybody. So see you next week, and just try to work out the solution, and we'll discuss the solution.
Sure, sir.
Okay.
Thank you.
Yeah, thank you.
Thank you, sir.